Hello, I am Dr. Fergus Donahoe, and in this video we're going to be looking at how to prove disjunctions with conditional proof. A disjunction, you may remember, is an OR statement, and to prove it we follow three simple steps. We want to prove the equivalent conditional, we want to convert that to a disjunction, and then double negate where appropriate. You are currently watching For the Love of Wisdom, my YouTube channel on free thought, philosophy, and critical thinking. And besides doing videos on logic, I do videos on science, on ethics, on religion, and on happiness. This video is part of a series of videos on symbolic logic. The very first video talks about what makes an argument a good one. And one of the things it covers is that a good deductive argument should be valid, which means that its premises should entail its conclusion. And that's what we focus on for the continuing videos here. We look at argument forms where if an argument fits that form, the conclusion has to follow from the premises. So first of all, we looked at the rules of inference, which are very simple rules concerning some operators like the and sign and or sign. Conditional, which means if-then, and we have dilemmas here. And then we went on to rules of replacement. These are rules for saying that if we have one expression that has the same truth value as another, we can replace it with what has the same truth value. And we can do that inside of a line, not just inferring from other lines like we do with the rules of inference. So the rules of replacement would let us replace part of a line. And these are expressed as biconditionals. A biconditional is equivalent to two conditionals, as you can see in this expression of the rule of material equivalence. It's saying that P if and only if Q has the same truth value as if P and Q and if Q then P. And more on that later. Then we started doing proofs with the rules of inference. And then we moved on to doing conditional proof, which is a method for letting us prove a conditional by assuming it's the if part, what we call the antecedent, and deriving the then part, which we call the consequent. And we started doing proofs of the rules of replacement here. As I mentioned, each rule of replacement is a biconditional, and that biconditional is equivalent to two conditionals. So we would use conditional proof to prove each conditional that a certain rule of replacement was equivalent to. And then we would conjoin those together with this rule here, conjunction. And then we would use this rule of material equivalence to get our biconditional. And then to save a step here, we introduced some new rules of inference for biconditionals. We have biconditional introduction and biconditional elimination. And this lets us save the step of putting it in this conjunctive form before concluding the biconditional. Then we looked at an example of nesting conditional proofs. Conditional proofs can be nested within each other. You can start a conditional proof, and before finishing it, you can start a second conditional proof, and before finishing that, you can start a third one, and so on. But each conditional proof has to be closed before you can close the conditional proof you started it in. Okay, so these are the previous videos in this series, and if you're new to symbolic logic, you might want to start with some earlier videos. And now we will continue with proving disjunctions with conditional proof. And I want to start here with the rule of material implication. We're going to be using this when we try to prove a disjunction with conditional proof. This rule shows that a disjunction of a certain form is equivalent to a conditional. And let me show you a truth table for this. We have if P then Q on one side, and that is true in three places, but it's false where the antecedent is true and the consequent is false. Remember, this is a material conditional. It's just about the relation of truth values between P and Q. So it's false whenever P is true. Sorry, it's true whenever P is false, I should say. Yeah, it's true whenever P is false. And it's true when both are true, but it's false in this case because, let's say, if P then Q, and, well, if P is true and Q is not true, that wouldn't make sense. Like, if I say, if you give me money, I will give you this product. If you give me money and I don't give you that product, then apparently that's not true. Okay. Now we also know that a disjunction is true in 3 places. It's normally true wherever either disjunct is true. And it's false where they're both false. So like the conditional, it's true in 3 places. And we can make a disjunction equivalent to a conditional by adding a tilde to one of the disjuncts here. Here we add it to the first one. And now where it's true lines up with where the conditional is true. So where, let's see, here, not P or Q. So not P is false, but Q is true, so that's still true. Here, not P is false and Q is false, so it's false here. But here, Q is true, and here, P is false, so not P is true. So it's true there and there. So you can see if P then Q is materially equivalent to not P or Q. We're not going to do a formal proof of this rule just yet. We will in a later video, and I want you to try to do a proof of this in anticipation of that video. That video is going to be introducing a new method for doing proofs that we don't have yet, but which we need to actually prove this. And now let's move on to the meat of this video, how to prove a disjunction with conditional proof. So here's what we do. First, we start by assuming, if we want to prove not P or Q, we assume P. P is the negation of not P. And we derive Q, and we get the conditional if P, then Q. So that's the conditional that the disjunction is equivalent to. And then we just use material implication to get the conditional we were looking for. But let's say we want to prove P or Q. Well, to do that, we would assume not P and derive Q. Then we get the conditional if not P, then Q. Through material implication, we would get not P or Q. And then we just use double negation to get P or Q. So double negation is not always necessary. You can sometimes go from a conditional to a disjunction in only 2 steps, just conditional proof and material implication. But sometimes you need the double negation. Okay, now in this video we're going to do a couple proofs. These are of the disjunctive forms of commutation and association. And let me show you what each of those are. So here's the rule of commutation in its disjunctive form. P or Q is materially equivalent to Q or P. And here is the rule of association in its disjunctive form. P or parentheses Q or R is materially equivalent to parentheses P or Q or R. And this is just saying that when you have a string of disjuncts, you can move the parentheses around and it doesn't change the truth value. It's still going to be true if any disjunct in there is true. So if you would like to, you might stop the video now, try to do the proofs on your own, and then come back to watch the solutions in this video. And at the end of the video, I will assign some problems for you to try before watching the next couple videos. We're beginning with a proof of the rule of commutation, and before I continue, let me say that this solution is also going to be in the blog post for this video. You'll find the solutions to both of the problems there. And the link to the blog post will be down below. You can go check that out. You will also find there links to blog posts on other videos in this series, as they each have their own blog post on my blog. Okay, so we want to prove P or Q is equivalent to Q or P. So we're going to start by assuming what we have on one side of the conditional of the biconditional. We assume P or Q, and we want to prove Q or P. So we're going to start by assuming not Q, because this is going to be equivalent to the conditional. If not Q, then P. So there's our assumption, not Q. And now we want to get P, so we can do that through disjunctive syllogism. And then we get if not Q, then P through conditional proof from lines 2 and 3. Very short conditional proof. Through material implication, we get not Q or P. And then through double negation, we get Q or P. And we can close off this conditional proof, and we get if P or Q, then Q or P. And now we want to do the same thing in the other direction. So we assume Q or P, and we're going to try to prove if not P, then Q. So we assume not P. We get Q through disjunctive syllogism on lines 8 and 9. And then through conditional proof, we get if not P, then Q. Then we get not P or Q through material implication, and then through double negation, we can get P or Q. And then through conditional proof, we get if Q or P, then P or Q. And then through biconditional introduction, we can get P or Q is equivalent to Q or P. So that was a very quick, simple proof. And now let's move on to a proof for association. We start by assuming what we have on the left side of the biconditional we want to prove, which is P or parentheses Q or R. And we're going to try to prove parentheses P or Q or R. So let's start by assuming the negation of the first disjunct in this disjunction. And that is not P or Q, the denial of P or Q. So we now have a second assumption nested within our first assumption. And then through De Morgan's, we can get not P and not Q. And we can simplify that to get not P. And now that we have not P, we can use disjunctive syllogism to get Q or R. And that's going to let us do another disjunctive syllogism. First we need not Q, which we get through simplification on line 3. And now another disjunctive syllogism gives us R. And R is what we were looking for. So we can now end this conditional proof, and we get if the negation of P or Q, then R, from lines 2 through 7. Now we use material implication to get not P or Q or R. And we use double negation to get rid of the two negation signs. And now we have parentheses P or Q or R, which is what we were looking for. So now we can close off this conditional proof, and we get P or parentheses Q or R, then parentheses P or Q or R. Now we just want to do the thing in the other direction. So we assume what we have on the right side of the biconditional now. We get P or Q or R, where P or Q is surrounded by parentheses. And we're going to want to try to prove P or parentheses Q or R. So should we assume P here? If we did assume P, there's not much we could do to get Q or R. So we're not going to do that. Instead, we're going to assume not Q or R. All right, let me back up here. If we assume not P, there wouldn't be much we could do. We're going to assume not Q or R instead. And that allows us to use De Morgan's like we did up above, and we get not Q and not R. We get not R through simplification, And that lets us use disjunctive syllogism to get P or Q. And then we simplify to get not Q and do another disjunctive syllogism to get P. That lets us close off this conditional proof, and we get if the negation of Q or R, then P. Through material implication, we convert this into a disjunction, which is not Q or P. And then through double negation, we get rid of the two negation signs, and we have almost what we're looking for. We now want to put P on the left side, and we do that through commutation. And now through conditional proof, we have if parentheses P or Q or R, then P or parentheses Q or R. And finally, through biconditional introduction, we can get the biconditional that we were looking for, the disjunctive rule of association. Okay, for the next couple of videos, I'd like you to try to do proofs for the rule of distribution. It has two different forms. Try to do each one. I'll cover them both in the same video. And I'd also like you to try to do a formal proof of material implication. I will warn you ahead of time that we don't yet have the tools for doing this. But we will be introducing a new rule that will help us prove this. But see how far you can go with a proof of this. See where you get stuck in it. And that will prime you for learning what we're going to talk about in a later video. Okay, so in upcoming videos we have proving distribution with conditional proof, and we have introducing indirect proof. Thank you for watching. Check out the blog below. And if you're interested in philosophy or free thought, go ahead and check out some of my other videos.